Okay, in this lecture, we're going to discuss sections 10.3 and 10.4. The first section, 10.3, will discuss work and power. So when a constant torque acts on a rigid body, and that undergoes an angular displacement from theta 1 to theta 2, then the work done by the torque is going to be equal to the torque times the displacement, the angular displacement. When the object rotates with angular velocity omega, the power P, the rate at which the torque does work, is going to be the torque times the angular velocity. This is a particularly interesting bio application of what's going on in your inner ear. You have canals that are oriented along three spatial axes, and in response to angular acceleration, the canals and the sensory cells they contain rotate relative to the internal fluid, and that motion is detected by the cells and converted to electrical signals that are sent to the brain. So, suppose a tangential force with constant magnitude F acts at the rim of a merry-go-round platform with radius r. You can see that here. While the platform rotates through an angle, delta theta, about a fixed axis during a small time interval, delta t. The displacement of the point at which the force acts is delta s. So we've got our displacement going on here of delta theta, and the arc length that is traced out is going to be delta s. The relationship between delta s and delta theta is right here. So by definition, the work done by the force is going to be the tangential force times the change in the arc length. And if it's measured in radians, it's going to follow that if we replace that length by this expression, that this is what we would have as far as work is concerned. Now, the tangential force times the radius is going to be the torque due to the tangential force. So, change in the work is going to be equal to the torque multiplied by the angular displacement. And if the torque is constant while the angle changes, then the work done on the body by the torque is going to be defined by this. The work is in joules, torque is in Newton meters, and the angle theta is going to be in radians. So this equation is the rotational analog of work is equal to the perpendicular force times the distance displaced. And the force in figure 10.14b is no radial component. If there were such a component, it would not do work because the displacement of the point of application has no radial component. A radial component of force would also make no contribution to the torque about the axis of rotation, so it's correct for any force even if it does have a radial component. Since the change in work over the change in time is the definition of power, this is going to be the rotational analog that goes along with it. That's going to be the same as the torque times the change in angular displacement over the change in time. So that's going to be our definition of power. Power is going to be equal to the torque times the angular velocity. So in the relationships that we've derived, angular displacements must be expressed in radians and angular velocity is in radians per second. Angular momentum, section 10.4. The angular momentum with respect to the axis through the point O of a particle of mass m and velocity v is going to be mvl. Let's take a look here. So we've got our arm here that's going out. It's the length of r. We've got the momentum being applied here. And L is going to be r times the sine of theta that's in between r and p. So that's why when you take a look at this, the momentum is mv, and the L is going to be the r times the sine of theta. So we're looking again at what is being applied perpendicularly here. So when a rigid body with moment of inertia I rotates with angular velocity omega around a stationary axis, the angular momentum with respect to that axis is going to be the moment of inertia times the angular velocity. In terms of torque and angular momentum, the basic dynamic relationship for rotational motion can be restated as the net torques is going to be equal to the change in angular momentum with respect to time. So we've got some good real world examples here of what's going on with this. So we've got an Olympic ice skater with outstretched arms, sends himself spinning around a vertical axis. When he pulls his arms into his sides, he spins faster. So when a diver goes off the high board in a layout position and then pulls her knees in towards her chest into a tuck position, she's going to spin faster, even though there's no appreciable external torque acting on her. A little bit of wind resistance, but not much. So both of these familiar phenomena, as well as many others, can be understood on the basis of a quantity called angular momentum. So again here, angular momentum is going to be the moment of inertia times the angular velocity. The units of this are going to be kilograms times meters squared divided by seconds. This angular momentum is going to be the rotational analog of the linear momentum. The angular momentum is positive for counterclockwise rotation and negative for clockwise rotation. So the basic dynamic principle here is that the net torques is going to be equal to I times alpha and can be restated in terms of the angular momentum. If the axis doesn't move within the rotating object, then this is constant. And in that particular case, alpha is going to be the same as the change in omega with respect to time. We can bring the moment of inertia in here, it doesn't matter. But if we do that, then we end up with the angular momentum. So the rate of change of angular momentum of a rigid body with respect to any axis equals the sum of the torques of the forces acting on it with respect to that axis. If the change in torques is equal to 0, then the angular momentum is constant and does not change with time. If the angular momentum of a rigid body is constant, then the sum of the external torques on that body must be 0. So we can also define angular momentum for a single particle. So we've got our figure here. A particle moves in the xy plane. Its radial and tangential components of velocity are shown. The instantaneous velocity and linear momentum of the particle lie along a line that's perpendicular distance L from the axis through this point. So we can define the angular momentum of this particular particle as follows, which is what we had gone through in the summary. So we've got some discussion here regarding the directions of the velocity and momentum. Then they correspond to a counterclockwise positive rotation, which is what you're seeing here. The distance L serves as a moment arm for the velocity. and it's analogous to the moment arm of a force and the definition of torque. Equation 10.11, let's see, there we go, is consistent with the original definition of angular momentum. So suppose the object consists of a collection of particles with these masses at a distances of these from the axis through the point O. For each particle, the angle phi is 90 degrees, so the moment arm is the distance RA from the axis of rotation. When the object rotates with the angular velocity omega, the magnitude of the velocity of point A is going to be equal to this. And the angular momentum, if you make some substitutions here, comes about, and this should start to look familiar. If the object is rigid, all of the particles move at the same angular velocity, which means that if we sum all of those together, then we can come up with a moment of inertia times the angular velocity. So got some more exercises down there for you to work through.